There's a new, super popular, nature-inspired autonomous agent system floating around on YouTube. So we have to cover and rebuild it in Houdini, right? Before we do anything though, let's give credit where credit is due. Particle-Life was invented back in 2017 by Jeffrey Rentrella. However, I first learned about the algorithm in two beautifully produced videos by Tom Moore, and it's also his implementation that I used as a guide here. All links are in the description, and I highly recommend you check them out as well. But now let's talk about Particle-Life. So, as you might have guessed, Particle-Life is based around particles, and those particles can basically do two things. They can either be attracted to other particles, or they can be repelled by other particles. That's all they can do. What makes all of this interesting is different particle types. We group our particles into different types, and a particle that we're currently processing will act differently depending on what types of particles are near it. So for example, orange particle here might be very strongly attracted to other orange particles. It might be a little less attracted to blue particles, and it may be very strongly repelled by those green particles right here. And overall, this leads to a lot of movement vectors, and a particle will probably move into this direction in the end. If you want to summarize all the different behaviors between particles, we can do this in a way that looks something like this in a matrix. Here we have all the particles that we're currently taking a look at, and here are all the particles that this particle in this line right here will be reacting to. And if we have a very positive value in one of those fields, this will mean that a particle is very much attracted to that other particle. If we have a negative value here, that means that a particle will be retracted or repelled. And if we have just a 0 here, that means that both of those particles won't act between one another. There won't be any forces to speak of. Now, the interesting thing about this behavior matrix here is that it allows for asymmetry in our system. So if we, for example, focus here on the interactions between an orange particle and a blue particle, or a blue particle with an orange particle, we can see that an orange particle, if it takes a look at a blue particle, will be attracted to that blue particle. However, if a blue particle takes a look at an orange particle, it will be repelled by that particle, because here we have a positive value and here we have a negative value. And just by looking at this and thinking about this, you can probably guess that this will result in something that almost looks like orange chasing blue. And this is actually pretty much all there is to particle life. This is all what drives this beautifully complex behavior in the end. But still, we need to take a look at how we want to implement this in Houdini. So like we so often do in Houdini is we process each particle individually, for example in a wrangle. And for each particle, we want to search for other particles around a certain search distance, like this. And we want to process each and every particle that happens to live inside that radius. And for each particle, let's for example take this green one here, we want to find out 3 things, or we want to get 3 different types of information. We want to get the direction from a main particle to the green particle. We want to get the distance between both of those particles, and we want to get the particle type. So in this case, this is a green particle. And we want to combine these 3 informations right here. We want to combine those into a force that in the end drives the behavior of a main orange particle. And in this case, the force will be a slight attraction towards that green particle right here. Now, there's one part of those 3 infos that's pretty simple. That's the direction. This is a vector that points from a main particle to the particle that we're processing. The interesting bit about this whole algorithm is how we can combine the distance and the type of this particle that we're processing into the strength of the force that we're going to apply in the end. And this is what we're going to take a look at next. We can derive the strength of the force in the end by a graph that looks like this. And there's a lot to take in here right now. So let's do this step by step. First of all, at the very origin of this graph, we have a main particle, orange particle. And somewhere on the x-axis of that graph, we have the particle that we're currently taking a look at, our green particle. And the distance from that green particle to the origin or to orange particle is the same distance as in 3D space, the distance that we measured. So if we want to find the strength of our force, we just have to move to the position of our green particle here. Then we need to go up or down until we intersect with our line here. So in this case, this is this position right here. And then we go back to our y-axis, and in this case we're in the positive section of our y-axis, and this means that our orange particle will be attracted to that green particle. If our intersection would lie somewhere in the negative y-axis, then our particle here would be repelled. These are the basics of the behavior. Let's quickly take a look at how we can create this curve, this function that we're looking at here. And first of all, we can divide this graph here into 3 sections. We have this beginning section, this middle section, and this end section. Let's start first of all in the beginning. This goes from a distance of 0 right on top of our main particle to some minimum distance that we want to set in our algorithm. And in this section, no matter what type of particle we're taking a look at, we're always repelling from our main particle. And this part of this line of this function is just there to keep the particles apart so they don't collapse all into one single position, one single particle. And this is how we get those nice blobby shapes in the end. Then, after some maximum distance that we're also going to set in our code, our graph here is just a flat line around 0. So we won't apply any forces to our particles here anymore. They won't act on each other upon that certain distance. And between the minimum distance and the maximum distance, we have this V shape that can be either positive or negative. And this will in the end be what drives the interaction between particles. And again, a very positive V will result in a very strong attraction, and a very negative V will result in a very strong repelling force. And where do we get our V shape from? Well, again, it's this matrix that we talked about earlier. We can take a look at the particle that we're currently processing. This is an orange one. We can take a look at the particle that we're taking a look at here. This is a green one. And on this area in this matrix, this is a value of 0.5. So we're definitely in the positive range of this middle part right here. So again, we're attracting. And this value right here controls the peak of this V shape in the end. So this is all we need to know about the theory of this algorithm. Let's now finally jump into Houdini and implement this. Let's start out with an empty scene. Let's drop down a geocontainer. Let's jump inside. Let's maybe make the parameters a bit smaller. And let's first of all drop down a grid. A size of 10 by 10 is fine. And on this grid, I want to first of all scatter some points. And in this case, I want to start with a lot of points, and let's make it 20,000 like this. Next, I want to create a attribute on my points that will encode the type of point that we're processing. So for this, let's use a point wrangle, and I just want to apply the type randomly for now. So I at type is equal to a random function driven by our at ptnum. And since the largest matrix that we can easily create in Houdini is a 4x4 matrix, I want to create 4 different types of particles. So to get to a value range between, in this case, 0 and 3, let's take all of this and multiply it by 3. Let's also round all of this to an integer. So in front of a rand function, let's put in an rint function, and in case all of this in parentheses. And in front of this, to finally convert a float here into an integer, let's also use an int function around all of this. And now we're done here. Now we should have a type attribute on our points. And let's quickly color those points in by our attribute. So let's drop down a color node for this. Set this to random from attribute, and let's choose a type attribute right here. And to make all of this a bit more visible, let's maybe hit D to bring up our display options, and let's set the background first of all to dark. And let's maybe play with the seed to get a better separation between particle colors. Yeah, a value of 1.06 looks a lot more pleasing to me. Also, let's make those particles a bit more visible as well. Let's drop down a visualize node, in this case a visualize properties node. And in here, I want to turn on points as spheres, and this will make our particles a little bit more visible again as well. And this is actually all our prep work in SOAP's done. So now let's drop down a pop network and build our main particle life system in here. First of all, in our popnet, let's work on our source. First of all, I want to turn off guide geometry here. I want to bring in all points, and I want to bring in all my points just on the first frame of our simulation. So it's in here, right, $f double equals 1, like this. And now we have all our particles in our particle simulation. What I want to add in here next is a pop drag force, where this in here, and I want a lot of drag in the simulation, which will make sure that our particles are behaving the way we want. So let's turn up the air resistance to a value of 10. And now finally, let's drop down a pop wrangle, where this above our pop drag force, and in here we want to implement our particle life. On this pop drag, I want to go to the inputs tab, and I first of all want to set the first input to myself, to the particles, and now I can start coding. So let's hit Alt-E, let's enlarge this, and let's start writing our code in here. First of all, I want to create all my parameters to control my simulation. And first of all, I want to create the behavior matrix. Let's get a matrix variable, call it params. And this should be equal to a matrix parameter. And let's call it parameters, like this. Then we want to set the minimum and the maximum distance for our force function. So let's create, first of all, a float min_dist. And this will be equal to a channel float. And let's call this minimum distance, like this. And let's copy this. Let's call it max_dist and maximum distance, like this. Then next, I want to create a global scale for the force that I want to apply to each particle, sort of a speed control for the entire simulation. I want to call this force_scl, force scale. And again, this should be a float slider called force_scale, like this. These are parameters. Let's quickly hit apply here, and let's hit this button right here to create our parameters. And for now, I want to quickly enter some basic values. For our minimum distance, I want a value of 0.3. For my maximum distance, I want a value of 1. And for my force scale, I also want a value of 1. And for my behavior matrix, I first of all want to set it in a way so that each type of particle attracts into a ball. And I can do this simply by leaving all values here at 0. Just this middle diagonal line. In here, I want to enter just a series of 1s, like this. Now let's keep working on our code. First of all, I want to search for all my neighboring points. So this will be an integer array called npts. And I want to use the nearPoints function for this on geostream0, looking for my current position. And I want a search radius of my maximum distance. And I also want to search just for a maximum of 100 points. This is something that made my simulation run a whole lot faster and didn't really result in any noticeable quality losses. So let's add this in here as well. And let's close this. Now in this array is also the point or the particle that we're currently processing, and we don't want this. So for this, let's use a remove value function, and from our npts array, we want to remove our current ptnum, like this. Next, I want to create a vector to store the global force in the end in. And this is a vector that in this case I called acceleration, and I want to set this vector from now to a value of 0, 0, 0, like this. And now let's finally write a for loop, and let's process each neighboring point. For this, I want to use a for each loop. Let's store our near point in a variable called npt. And this should be grabbed from our near points array, like this. Then in our array, we first of all want to find out what type our near point is and the position of that near point. So int and type is equal to a point function on geostream0, taking a look at an attribute called type on our npt point, like this. Let's grab the position as well. This will be a vector. This will be called npos. This will again be a point function, but in this case, we're going to search for the p attribute, like this. Then once we have the p attribute, we can find the direction and the distance. So for the direction, let's create a vector called dir. And if you know your vector math, you know that we can get the direction by subtracting vectors. And this will be a position of the near point minus our own position, so minus v at p. And once we have this direction vector, we can also get the distance by just measuring its length. So float dist is equal to the length of our dir vector, like this. Now we have the three different things that we need for our force in the end. We have the near points type, we have the direction, and we have the distance. Let's now work on implementing our function. And I want to take a somewhat hacky and somewhat lazy approach to this. This can certainly be optimized a whole lot, but this is a whole lot more easy to write. First of all, I want to check if I'm smaller or larger than the minimum distance. So if our dist is smaller than our min dist, then we just want to repel all particles based on their distance. So let's reuse our dir vector right here. And this should be equal to our normalized dir vector times a fit function. In this fit function, we want to pass in our current distance, and this again should go from 0.0 to our min dist. And to get a very strong repelling force, we have to add in a very negative value in here. So in this case, let's choose minus 10.0 like this, and this goes to 0.0 at the min dist point. And then we take all of this and simply multiply it by our force scale, like this. This is our first part of a function done. Let's work on the second part. So for all other cases, we again want to modify our dir vector. And again, this will be based on our normalized direction. Now we have to implement this V shape in the end. And for this, I'm again going to be lazy and I'm just going to use a ramp parameter. So let's use a channel ramp for this. Let's call a ramp shape. And I want to drive this ramp with a variable called ramp pause that I want to create later. And this will be a V shape in the end. Then we have to multiply this V shape by the right value from our behavior matrix. And for this, we can use the getComp function. And let's maybe make some room here. And our matrix is something we call params. And we first of all want to take a look at our own index. So I at type, this will be the right column. And then our n type, and this will be the right row in our matrix. And then finally, we want to take all of this and again multiply it by our force scale. Something like this. Now to make this ramp parameter work, we first of all have to create this ramp pause variable. So let's create this as well. So float ramp pause is equal again to a fit function. And we put in our distance, and this goes from our min dist to our max dist. And the output values will be between 0.0 and 1.0, the value range that our ramp expects. Like this. This is our function done. We don't have to worry about what happens after our max dist because we also use this in our near points function as a maximum distance. So these points will be processed at all. And we can close all our parentheses. The last thing that we need to do in our loop in here is add the direction that we calculated to our acceleration. So let's write acceleration plus equals to dir like this. Then let's close our entire loop. And finally, to make this all move inside our simulation, we have to write this to a force. So v at force is equal to our acceleration. And to make this compatible with other pop forces in here as well, we have to write not equal but plus equal in here, because we always add forces to our main force in a simulation, like this. And this is our whole algorithm done. So not much code at all. Let's hit apply in here again. There's one typo that I made here. This is called npts, not ntps, like this. Let's hit apply again. Now this should work. And then we have to hit this parameter button in here one last time to get our function in here as well. And in here we want to create again this V shape. So let's take the AND handle in here, this at a value of 1, and move it to the middle to a position of 0.5. And let's AND in here with another handle at 0. And again, this will create this V shape. And now we can keep our fingers crossed. We can hit play on our timeline. And for this simulation right here, I found it necessary to make this timeline very large. This sims quite fast, and you can simply use something like a time shift node in the end to speed things up or slow things down as you like. But we should very soon see, again as we expect, our different particles organizing into different cells. So this all seems to be working. Let's maybe try to create a more interesting thing right here. Let's maybe turn off the attraction for the last two types. Let's keep the attraction for the first two. Let's also maybe make our first type very attracted to the second type. Let's see how that looks. Give it a second to organize. And now blue is very much attracted to red. And let's maybe also make red a bit afraid of blue. Let's maybe add a value of -0.5 in here. And as we can see, we get quite an interesting behavior in this simulation in the end. And you can play around with all of these values as long as you want and get different and interesting behaviors. And also in the scene files, you will find one setup that uses a bit of Houdini tops, a bit of PDG to randomly fill out these fields, so you can quickly try out different setups and see where this leads you to. But this is all I have to say for today, and until next time, it's cheers and goodbye. If you like what we're doing, please consider becoming a patron of ours, not only for supporting Intagma, but for access to in-depth courses on topics such as KineFX, Vellum, Vex, Python, and so on and so forth. Also, let me say thank you so much to all our existing patrons. Without you, this channel would not be possible. Thank you.